Let's say that I wanted to solve this trigonometric equation, and there's a twist. I need to find all the real solutions to this equation, and I need to find only the solutions that are in this specific interval. Now, how that's going to work is we are going to write down all of the solutions in a list and then pick out the ones that we want. This equation needs to be solved in a specific order. First, we need to subtract 3 from both sides. Then we need to divide by 3 on both sides. And then it's time to deal with the trigonometric function. I need all of the places on the unit circle where the cosine function gives you a value of -1, and there's actually only one of those, and it's 180 degrees or pi. And so that means that x is equal to pi plus 2 pi k, where k is in z. Those are all of the angles that point directly to the left with the terminal edge. So, what I'm going to do is I'm going to write this list of angles in list form. Now remember, that means that you're going to take k to be certain integer values that you like. You're going to substitute -1, 0, 1, 2 for k, and you're going to write out all of your solutions as a list. I like to make sure that I'm writing down plenty of solutions. Write down a lot of them. It can't hurt. Now that I have things in a giant list, and I get pi, 3 pi, 5 pi, 7 pi. So this list is all of the odd integer quantities of pi. This is going to help me see which solutions lie in the interval and which do not. So I'm looking for only solutions that are between 0 and 6 pi, and right now it's really obvious to me that pi, 3 pi, and 5 pi are the numbers that I want. I throw out the rest of the solutions. This equation has exactly 3 solutions that lie in the special interval. So one more example for good measure. Let's say I want to find all the real solutions of tan x equals 1 inside of the interval -2 pi to 2 pi. First I have to ask myself, where does the tangent function give me +1? Now there are really 2 locations where this happens. There are 2 places where the x and y coordinates on the unit circle are equal to each other and you get +1. There's one in the first quadrant and one in the third. And so this location corresponds to pi over 4 on the basic unit circle, and this location corresponds to the angle 5 pi over 4. And so what I can do is I can tack on the plus 2 pi k to both of these to indicate that I'm saying all the coterminal angles also. And so this really is the full and complete solution set to this equation. Now, I want you to notice something. If we were to start here and take a walk around the unit circle in the positive direction, I would bump into a new solution every half a cycle around. Every time I go forward pi radians, I hit a new solution. And so we have pi over 4, 5 pi over 4, 9 pi over 4. They're all evenly spaced. And so what that means is I can simplify these 2 sets that I wrote with indexing notation into one because the solutions are evenly spaced. They're spaced apart by pi. They happen every pi, and so I can grab any one solution and put plus pi k, and so that's how I can simplify it. That's entirely optional. You get to do that if you want to. Now, why did I choose to do that? Because I felt it might be easier for me to write down all the solutions in list format, which is what I'm going to do right now. I'm going to write down pi over 4, and then I'm going to start adding and subtracting multiples of pi, or 4 pi over 4, to generate a whole bunch of different solutions. Now that I've written all of these down in list format, it's really easy for me to see which ones are in between the numbers -2 pi and 2 pi. So for example, notice how 9 pi over 4 is way too big because 9/4 is bigger than 2. And similarly, -11 pi over 4 is way too low because -11/4 is below -2. So it turns out there's going to be exactly 4 different solutions. Discard all of the other ones. There are 4 solutions to this equation.